Hello everybody, this is Professor Lombardo. In today's lecture, we're going to talk about a more realistic version of the confidence interval from last time. We're still going to be using this confidence interval to estimate a population mean, but we're going to make a couple of minor tweaks that'll make it a little bit more useful in practice. So in this course, I'm presenting you with three main types of confidence intervals. The first one, which we went over last time, is a confidence interval for a population mean, with the sort of unrealistic expectation that your population standard deviation is known. It's information that you have available to you, right? It's unrealistic, but the main reason I presented it to you is because it's informative. It's a nice example that shows you the connection between the central limit theorem and how these confidence intervals are actually created and why you can guarantee a certain confidence in the fact that your interval really does contain the population mean. Let's just go over our steps. Remember, the general idea is you'll be provided with a confidence level, the population standard deviation, and typically some sort of sample data where you can use that sample data in step 2 to compute X bar. This is your best guess for what the population mean is. But remember, while it's close, it's not exactly equal, so we need to widen by a margin of error. From the provided confidence level, you can find alpha over 2, and then our critical z-score z alpha over 2. Using z alpha over 2, we compute our margin of error, combining our standard deviation from the central limit theorem, multiplying by our critical value. And then finally, to actually create that confidence interval, we take our best guess, our sample mean, and we subtract the margin of error to get the left bound, and we add the margin of error to get the right bound. And this gives us a region where we expect our population mean to fall with the confidence level as a success rate for how confident we can be that the real population mean falls in that little region. Now, the issue here is that this particular confidence interval requires that we, for some reason, know ahead of time what the population standard deviation is. We don't typically know this information. In fact, we typically don't know much about the population we're trying to study. That's why we're trying to study it. So, what we're going to see from this point forward, now that we've used that type of confidence interval from last time to understand where these things come from and how they work, we're really primarily just going to work with this new version that we're going to present today. This is a more realistic version for researchers. This is what people actually do in practice. This is a confidence interval for a population mean, right? So we're still estimating the same parameter. But this time, we're going to relax the assumption that we happen to know the population standard deviation. The general idea is to use the standard deviation for the sample we collect, a sample standard deviation, instead of sigma. And this comes at a small cost, but most of the mathematics behind how this new confidence interval works, we're going to kind of brush under the rug and say it more or less follows the same type of idea that we saw in the previous case, but just with a new probability distribution. And this is something called the student's t distribution. Okay, now before you get too nervous, oh no, another probability distribution that I keep track of, don't worry too much. The t-distribution you can think of as just sort of like a modified normal distribution. It almost looks exactly the same in its shape. We'll take a look at it in a second. And the way that you work with it in Excel is basically the same as well. Rather than saying using a norm.dist or a norm.inverse, you'll use t.dist or t.inverse. So you'll see that the changes in working with this modified or this new t-distribution is very minimal. It's nothing to be terribly concerned about. Visually, you can even see how similar it is to the normal distribution. The main difference is that the t-distribution is sort of, there's a whole family of t-distributions, and they're kind of parameterized by the sample size that you're going to end up working with. And so what you'll notice is on small sample sizes, the t-distribution, which is in red here, has what we call fatter tails, which means that the values that are higher or sort of more to the right and more to the left are more likely than they would be with the standard normal distribution. But as your sample size increases, you'll notice that the student t-distribution, which is in red, kind of approaches the standard normal distribution, which is this black dotted line. So they're very similar in shape. In fact, we can kind of summarize some things to note about the t-distribution. It's very similar in shape to the standard normal distribution. It's bell-shaped with a mean of 0. Again, there are many different t-distributions, and it's characterized by a parameter called degrees of freedom. Degrees of freedom is essentially related to the sample size that you end up working with. So if you collect a sample of, say, 22, you'll have a certain t-distribution or red curve associated to working with that sample. For our purposes, degrees of freedom is always going to represent our sample size minus 1. As degrees of freedom gets larger, the t-distribution looks more and more like the standard normal distribution, and we've already started to observe this, right? When our sample size is very small, you can see a difference between the t-distribution in red and the standard normal distribution in black, but on a large sample size like 50, they're basically overlapping one another. The nice thing is to compute critical values, which is what we're going to be moving towards when we do our confidence intervals. We can compute t-scores with a certain area to the left using the t.inverse command. So it's not norm.s, which would be standard normal distribution, but now a t.inverse command. And we'll have an extra parameter here for the degrees of freedom. So this will choose essentially the right red curve based on our sample size that we should use when computing those critical values. Okay, so armed with our new probability distribution, the student t-distribution, we can start to describe our new confidence interval, or I should say really our modified confidence interval, because it's very similar to the last one with just some minor tweaks. The general idea, as we mentioned before, is to replace knowing the population standard deviation with a sample standard deviation instead. Now, typically these should be relatively close, and the cost we pay for using the sample information rather than the population information is we have to modify the probability distribution to the t-distribution. So the general idea is we're going to use S instead of sigma, and we're going to replace the z-score critical value with a t-score critical value, t alpha over 2. Where we used to do norm.s.inverse to find a critical value, we're now going to use t.inverse to find our critical value. Okay, so let's outline our slightly modified set of steps to do these confidence intervals for a population mean, this time where we don't know our population standard deviation. First, it's a good idea to keep in mind what you should be given, right? Typically, in a confidence interval process, you'll know the confidence level you want to use, right? The success rate you're shooting for, and you'll be given the sample data. From the sample data, we can compute x bar. Remember, this is our best guess for what our population mean is, but then we're going to widen from that best guess to create a confidence interval. To create that confidence interval, we'll need to know our sample standard deviation, we'll need to know our sample size, and we'll need to know our degrees of freedom. Remember, degrees of freedom is just your sample size minus 1. So n and df are kind of the same thing with just a minor modification. As before, from our confidence level, we can determine alpha and alpha over 2. Remember, alpha is the missing percentage, which we divide over 2 tails. And now instead of computing z alpha over 2, we're going to use t.inverse to compute a t critical value from the appropriate t-distribution. Using t alpha over 2, our sample standard deviation, n, and degrees of freedom to get that t-score, we're going to compute this new margin of error. Notice this formula looks exactly like the old one, but we've replaced z alpha over 2 with t alpha over 2, and sigma with our sample standard deviation. Finally, our confidence interval takes the same form too. X bar is still our best guess for what that population mean would be, and then we move to the left and to the right by this margin of error to create the confidence interval, which has a higher likelihood of overlapping with that population mean.